Hello everyone. In this lecture video, we will discuss the topic called fixed point iteration. So before that, let's go to our slide. This one here, and then it's not this presentation. Okay, so as you can see, in definition 38, this is the definition of the fixed point, and later we will know why the idea of fixed point is important in root finding. Okay, so it says here a number p is a fixed point for a function g of x if g of p is equal to p. Okay, so all you have to do is to solve this equation, and then that number is what we call the fixed point. So for example, let's go to our open board. Okay, this one here. For example, okay, determine any fixed point or points of the function g of x is equal to x squared minus 2. Okay, so let's solve this one. Based on the definition, if we go to definition 38, so you have to solve this equation. G of p is equal to p. Okay, so or let's say x, g of x is equal to x, and place x by p. So go back to our open board. Let's say since our function is g, so we will use the notation g. G of p is equal to p. So this one here we have p squared minus 2 on the left side is equal to p. So we have here p squared minus p minus 2 is equal to 0. So I think you can do factoring here. So we have p here, and then 2 and then 1. This is negative and this is positive. Okay, so what we have here is p is equal to p, or p is equal to negative 1. So therefore the fixed points, okay, fixed points of the function g is 2 and negative 1. Okay, so there will be a case when the given function do not have a fixed point. So what does this mean? Let's go to our Gizmo's graphing calculator. This one here, our website, and let's say Gizmo's graphing calculator and graph the function x squared minus 2. So we have here x squared minus 2, and then is equal to x. So what do we mean by the fixed point is that based on the graph, it is the intersection between the function g and the line y is equal to x. So as you have noticed here, we have -1 and +2. Look at the abscissa are the fixed points of G. Okay, so basically the fixed points are the intersection of the function and y is equal to x, or the line y is equal to x. So let's put a note here. Note a fixed point for G occurs precisely when the graph of y is equal to g of x intersects the graph of y is equal to x. Okay, so please do remember this this note here. Okay, so let's go now to our discussion. So how do we relate fixed point to our main topic, which is about root finding? So it says here we have two problems that are related to each other. The fixed point problem is you are going to find p such that g of p is equal to p, while the root finding is to find p such that f of p is equal to 0. So this is basic. So with this, as I asked before, why do we need to study fixed point when our main topic is about root finding? So now we can now formulate a root finding problem as a fixed point problem, and vice versa. How do we do that? For example, we assume we want to solve the root finding f of p is equal to 0. So our p here is a root. Define g of x is equal to x minus f of x. So our g here is our function g in definition 38, and we write it in this form, x minus f of x. And observe that if p is a fixed point, of g, then if you substitute our p here, we have g of p is equal to p, and we know that f of p is 0, so p minus 0 is p. So therefore p is a root of f of x. So if we get the fixed point of g and write the function, this one here, g of x is equal to x minus f of x, then and p also is a root of f of x. So it is a the number p is a fixed point, at the same time a root of the function f. Okay, so the question now is, here the function g is not unique. So remember that the function is not unique. You are going to get that function. So there are many ways one can represent the root finding problem f of p is equal to 0 as a fixed point problem. And as we learn later, not all will be useful to us in developing fixed point iteration algorithms. Okay, this is because maybe the choice of your g is not good. Okay, so that's why it fails to solve the root finding problem. So the question now is, how do we know if the fixed point exists, and how do we know that the fixed point is unique? Okay, and also, when do we know that the function g has a fixed point? Okay, so this theorem 38, is a theorem that we need to use in order for a function to have a fixed point. And if that function has a fixed point, then we also know if it is unique or not unique. Okay, So first is the existence of a fixed point. If the condition that the function has a fixed point is that if g is continuous on the closed interval ab and all the function values is also an element of the closed interval ab, meaning in the box, in that particular box, okay, we know that this interval for AB are is on the x-axis, and this interval here is on the y-axis. So the function values is if it is also an element of AB of the if this interval for all x in the domain, then G has at least one fixed point in the closed interval AB. So the condition is that G is continuous and g of x, the function values are also an element of this set or this closed interval. Then you can assure that the function has at least one fixed point. Okay, at least one fixed point. Second is for the uniqueness. If in addition, meaning to say g is continuous and this is also true, these two conditions are true, continuous, and g of x is an element of the closed interval AB, and you add this condition, the absolute value of g of x minus g of y, meaning the distance between the function value of x and y is less than or equal to lambda times the function value, the function, times the lambda times the distance between x and y for all the x and y in AB, and of course your lambda is between 0 and 1, then the function g has a unique fixed point. Okay, so let's try to illustrate that one in the open board. Let's have an example on how to determine if the function has a fixed point on the given interval. So let's go now to, and also if that fixed point is unique. Okay, let's go now to our open board. Okay, let's go to our open board, and then let's write something. Let's have a new page here, and let's have an example. Okay, example here, example, no, let's color here, example 43. Okay, okay, so anyway, if I am mistaken. Okay, so before we go to our illustration of Theorem 38, I saw that I am going to prove this. So before I am going to illustrate Theorem 38, let me first discuss Remark 39 and all those theorems for us to have an illustration on how to use Theorem 38. Okay, so I forgot that I need to discuss those things first. Okay, so anyway, before the proof and illustration, let's have this Remark 39. Let g be a differentiable function on the closed interval AB such that the absolute value of the first derivative of g is less than or equal to k for all x on the open interval AB for some positive integer k less than 1. Then the hypothesis of part 2 of Theorem 38 is satisfied with lambda is equal to k. So this means that by the mean value theorem, this is Theorem 4 of chapter 1. When we have a review, please open your notes to chapter 1, so about mean value theorem. So in part 2 of Theorem 38, as you can see here, you can replace your lambda by k, and as long as the first derivative of g for all x in the open interval ab is less than or equal to k. So by mean value theorem, I know that you are familiar with this one. Then you can replace. I think I'm going to show you. Let's say let's go to our Firefox browser, and then let's type mean value theorem. This one here, and try to open, let's say this one here, or maybe this one, Wikipedia. Okay, or this post online notes. It says here that rules theorem. This is the mean value theorem. If the function f of x satisfies these two conditions, this is very clear. Our f is g, and differentiable on open interval ab based on the assumption of remark where are you, 39, this one here. Okay, differentiable. So by the mean value theorem, this one here, so just cross multiply this one here and you will have this one here. So that's why we replace f and f by g, and b by y, a by x, and so on and so forth, and you can replace this one here. Okay, so that's what we mean by the mean value theorem. And since by the property of the absolute value, and since g prime of x is less than or equal to k, so you can replace it by this one here. So this remark is very useful. Okay, and then another one, this theorem describes how we can find a fixed point. So it says here that if as long as the function g is continuous and all the images are also in the closed interval ab for x in the closed interval ab, and this assumption also holds just like in theorem 38 for all lambda between 0 and 1, then the fixed point iteration, just like the bisection method, the Newton's method, we have this kind of formula, very familiar, P sub n. So for all n greater than 1, greater than or equal to 1, it will converge to the fixed point P, and the unique fixed point G of in the closed interval AB for any starting P sub 1. Okay, so it will converge. So this theorem also will be proven in the open board later. Okay, and since we are now ready, we also have this remark 41 and corollary 42 before we are going to give an illustration of theorem 38. Remark 41, theorem 40 still holds if the second condition is replaced by this one. So you can use remark 39, this one here, this one here. Okay, so corollary 42, it says that if G satisfies the hypothesis of theorem 40, then this is the error bound. Okay, this one here, there are 4 error bounds. You can choose depending on the given. Okay, depending on the given. We will use this one later, but we will prove maybe one of these corollary, and then I will give it to you later, or maybe one of these. also. Okay, so next is okay, before this one, let's forget this one. Let's move to example 42. Okay, let's illustrate first theorem 38. Consider the root finding problem. X cubed minus 2x squared minus 1 is equal to 0 on the closed interval AB. Write the problem is a fixed point problem. G of x is equal to x for some g. Verify that the hypothesis of theorem 40 or remark 41 is satisfied so that the fixed point iteration converges. And second is let the starting guess p sub 0 is equal to 1. Then we will use corollary 42 to find and that ensures an estimate to be accurate to within 10 to negative 4. So let's solve this problem in the open board, just like what I have promised to you before. Okay, so let's go now to our open board. Where are you? This one here. Then we have here example 42. Okay, so remember that the problem is first problem is to write it as a fixed point. Okay, so let's recall our given. So our given is we have here the root finding problem. X cubed minus 2x squared minus 1 is equal to 0 on the closed interval 1, 3. And then let's have here solution for number 1. Okay, sorry, for number 1. Let's say this one here, number 1. So number 1 is to write the problem as a fixed point problem. Okay, so please pay attention to this solution. There are several ways. Okay, several ways we can write this problem as g of x is equal to x. Okay, so first is maybe you are tempted to use this formula that I written before, like this one here, g of x is equal to x minus f of x. Okay, I write this one in the discussion of the before theorem 38 or definition 38. Okay, so I write that one. Maybe you are tempted to use that, but there's a problem if ever you will use that kind of method. But that's the first approach. Okay, so first is we have to let f of x, if we are going to use that method, g of x is equal to x minus f of x. So let x cubed f of x is equal to x cubed minus 2x squared minus 1 and p. Okay, and p be its root. Okay, so we will denote the root of our function f of x to be p. Since the degree is 3, then we are sure that the number of roots is at most n is equal to 3. Okay, this is in your abstract algebra. Okay, and then so what do we mean by this? That is, since it is a root, we know that f of p is equal to 0. Okay, and if we let g of x is equal to x minus f of x, just like what I have said or written before, then what will happen is the root, okay, the root p is also a fixed point, okay, fixed point of g. Okay, so since our f of p is 0, this one here. So the conclusion is p is a fixed point, of g. But the problem here is, however, this choice for g will not be helpful. Okay, helpful. The reason is that since g does not satisfy the first condition, of theorem. Okay, what theorem? You can also say theorem 38.1, or you can also use theorem 40. Okay, theorem 40, since g of x is not an element of the interval 1, 3 for all x in the interval 1, 3. So for example, we have g of, let's say, g of 3 is equal to -5, but not an element of the interval 1, 3. Okay, so if you look at the word theorem 40, this one here, theorem 40 number 1. Okay, it must be that all the function values for all x in the interval AB must be an element of AB also. Or if you look at theorem 38, it says that g of x must be this one here for all x. Okay, so then we are sure, okay, that it has at least one fixed point, even if you don't graph the function. But use this one here, theorem 40. Okay, so let's try again and go back to our open board. Let's try again another. Why is that? Why is it that we use another way. Okay, letter B. Remember that, as I've said, I write it here. There are several ways we can write this problem as g of x is equal to x. Okay, so that's the reason. Let's try another method like this one. Since p is a root for f, we have we can write our function. Recall this one here, x cubed minus 2x squared minus 1 is equal to 0, and replace x by p since this is root. 2p squared minus 1 is equal to 0, and write it this way: p cubed 2p squared plus 1, and then take the square root, cube root, both sides. 2p squared plus 1, and then this one here. So we have here p is equal to cube root of 2p squared plus 1. Okay, one there. So what happened now? Therefore, p is the solution to the fixed point problem. G of x is equal to x, where g of x is equal to this one here, 2x squared plus 1 raised to the power of 1/3. Okay, so just rewrite this one. So this is our p. If you can imagine, this is x, this is just we will write a bubble dot somewhere here. You can write this one as p is equal to g of p, or g of p by symmetry is equal to p. Okay, so our g of p is this side here, the right hand side. Okay, so replace x as a function, and then notice that, I don't know if you notice, if you use Theorem 40, we know that let's show Theorem 40, this one here, Theorem 40. Let's show that g of x is an element of this one for all x in the interval AB. Okay, g is increasing on the interval AB or 1, 3, and g of 1 is equal to, let's go to our Dismos graphing calculator. Let's have this one here. Dismos, no, not this one. Let's erase this one first. Okay, let's graph our function. 2x squared plus 1 close, and then raised to the power of 1/3, 1 divided by 3. Okay, so that's our function, and the line, so this is our fixed point. Okay, that one here. Okay, that's our fixed point. But let's also plot the endpoints. So x is equal to 1, x is equal to 3, x is equal to 3, and also x is y is equal to 1, y is equal to 1, and y is equal to 3. Okay, and let's have this color. Let's change this one by orange. Okay, and let's zoom in. Okay, so this is the x-axis and this is the y-axis, and as you have noticed, the graph of the function, the green one, the quantity of 2x squared plus 1 raised to the power of 1/3 is inside the box, this box here, this one. Okay, inside the box. Okay, and this is our fixed point. So let's try to capture that one maybe later. Okay, so g of 1, let's have this one to compute our g of 1. 2 times x, or times 1 close square plus 1, and then close raised to the power of 1/3. Okay, enter. So the answer is 1.44. Okay, 1.4422. Okay, let's go to our open board. 1.4422, 4957, 4957, and also g of let's compute g of 3, the endpoint. Okay, g of 3. Okay, so g of 3 is let's copy this one and replace our 1 by 3 and hit enter. So the answer is 2.6684. Go to our open board. 2.6684, 0.1684 Okay, so and then notice that where are you? The open board, thus we can say that our g of x is an element of the interval 1, 3 for all x in the interval 1, 3. So this concludes that it satisfies our G satisfies theorem, the first condition of theorem 40. Okay, how about the second condition? Okay, first is let's have the derivative. Okay, so let's have the derivative of our function. Remember, our function is this one here. This is a function. The derivative of the quantity 2x squared plus 1 raised to the power of 1/3 is 1/3. 2x squared plus 1, 1/3 minus 1 is negative 2/3. Okay, and then the derivative of 2x squared plus 1 is 4x. Okay, so simplify, you will have 4x over 3 times the quantity 2x squared plus 1 raised to the power of 2/3. Okay, so that's the derivative, and notice that g prime of 1 is let's go to our this one, our Desmos graphing calculator. So we have 4x. So before we write our x, which is equal to 1, let's type first the denominator. Quantity of 2x squared plus 1 close raised to the power of 2/3. 2 divided by 3, and then let's replace that one by 1, and also the numerator is times the quantity 1. Okay, so the answer is, it enter 0.64099. Go to our open board, is equal to 0.6409999809. Okay, and also g prime of 3, the right endpoint. So let's go to our Desmos graphing calculator and copy this one here and replace our 1 by 3. Okay. 1 by 3 and hit enter. 0.56, this one here, 17. So go to our open board, 0.5617, this is 17, 56, 17, 687, 687, 682. Am I right? 517, 687, 517, 687, 682. Okay. And before that, let's graph the derivative first in our Desmos graphing calculator, so that we can decide whenever this function value g prime of 1 is the choice for k in remark 41. Okay, So remark, if you go to remark 41, as you can see here, remark 41, where are you? This one here. The choice of k will depend on the value of the highest value of the first derivative evaluated at these points in the closed interval AB. Okay, so let's graph the function first, the derivative in this most graphing calculator. So we know that the function derivative is just like this: 4/3 times the quantity 2x squared plus 1 close raised to the power of 2/3, 2 divided by 3. Okay, I think this is the one. Okay, so if you look at the graph of the derivative, let's replace the color by, let's say, purple is okay, but let's try to make this one as 5 to make it bigger, or 10. Okay, that one. Okay, enter. Okay, so this is the graph. And then notice that if you zoom in, okay, it seems like the function is, this is for 1 and this is for 3. It is decreasing. Okay, but if you look at the graph here, this is the highest point. Okay, it seems like from 1 to this max, the what do you call this one, the maximum value of this of these values here is this point here, which is not g prime of 1. Okay, so we cannot say that our k is this choice here. Okay, 0.641, but there is a highest point somewhere here. Okay, so what do we do, that what shall we do to get that point? Okay, so let's go to our open board, and then remember in calculus 1, in the, I don't know if you remember about, let's try to solve it somewhere here. Okay, in the bubble thought, let's say, let's have a bubble thought here, bubble thought somewhere here. Okay, if you remember in your calculus 1 about the first derivative test, okay, recall about the first derivative test. Okay, in your calculus 1, this is in calculus 1. Okay, it says there that you have to, by the way, our function now is this function, which is the first derivative, we will determine the absolute maximum value. Okay, since the curve is clearly opens downward. Okay, so we will let the function f of x, which is equal to 4x over 3 2x squared plus 1 to the power of 2/3, this function here, and determine the what they call this one, maximum absolute maximum value of this function, where this is our first derivative. Okay, just to get the value of k. Anyway, let's get the derivative of our function. Maybe you can use the what do you call this one? You can use the first the quotient rule, but for me, I will write this one as this form: 4x 4 third x 2x squared plus 1 times negative 2 third. Okay, so that it will be much easier to get the derivative. So copy the first factor for x and then derivative of the second. We have negative 2 third 2x squared plus 1. Negative 2 third minus 1 is negative 5 thirds, and then derivative of 2x squared plus 1 is 4x close plus 2x squared plus 1, and then derivative negative 2 third. Derivative of 4 third x is 4 third, that one. Okay, so equate this to 0, and then let's factor. I think we have a common here. The common factor is 4 third, and then on the other side, this one here, common is 4 third. We don't have an x somewhere here. Okay, we don't have an x, so but 4 third is common, and also this one. Okay, so let's factor 2x squared plus 1, negative 2 third, and what remains on the first term, this one here, is x squared, this one here, x squared. Okay, x squared, how about the constant? This is negative 8 over 3x squared. Okay, 4 times this one here, 4 times 2 is 8, and x also. Okay. And then if we factor this one here, we have 2x squared plus 1 raised to the power of negative 1. Okay, plus 1. Okay, that one there, and let's try to make it somewhere here. So this one has no roots. Okay, this one here, no root, since 2x squared plus 1, if we equate this one to 0, we have a complex number. Okay, and this one also, I think there is a root for this one. So we have here negative 8 over 3x squared times this one is 1 over 2x squared plus 1 is equal to 0. Okay, and then we have get LCD. We have 3 2x squared plus 1, and then we have negative 8x squared plus, so divide this one by this numerator, so 8 squared, and this one here is plus 3 2x squared plus 1. and then we have here is 0. Okay, simplify. Again, the denominator do not have a root, so negative 8x squared plus 6x squared plus 3. Okay, that one. And then finally we have negative 2x squared plus 3 over 3 2x squared plus 1. Okay, and then in the numerator we have in the denominator the same argument. We have a complex number here. Okay, this one here, but in the numerator we can have 0 is equal to negative 2x squared plus 3. So we have 2x squared is equal to 3. Then we have x squared is equal to 3 halves. And then what we have here is take the square root both sides, this one here, and then multiply by 2 over 2 so that we can rationalize. And then we have here x is equal to square root of 6 over 2, or this is approximately let's go to our Dismo scientific calculator. Square root of 6 divided by 2, so we have 1.2247. okay, 1.2247 44871. Okay, so this is the value in the denominator in the x-axis here. So this is 1.22. Let's copy this one here. Okay, copy, and then go to our this most tracking calculator. X is equal to this one here. Okay, enter, and as you can see in the graph, this is the absolute maximum value, or the maximum value of the derivative of the function g. Okay, that one. So we cannot choose our k somewhere here because it says in remark 41 the k must be in the upper bound of all points in the first derivative. Okay, so if we plug in our value, this one here, let's copy. If we plug in this one, copy here, square root of 6, this one, paste this one here, enter. So the highest value is 0.64. So if we go back to our open board, sorry, this one here, our f of x, or since our f of x is our g prime of x, and g prime of x of square root of 6 over 2 is, based on the calculation, is 0.648 0537 657. Okay, so this is now our k. Okay, so this is our k. Okay, our choice of k. So put somewhere here in our bubble thought. One. Let's make this one somewhere up to the top. Okay. That computation for our maximum value. So just look at the graph. Okay, just look at the graph. So that's our k. Okay, and let's continue our g prime. If again, if you look at our graph, I don't know if you remember, in calculus 1 we write this one as let's say interval, and then we put value of x, value of x, and then we have here the value of x, and then we have f of x, and then f prime of x, and then conclusion. I don't know if you remember this table. If you remember that from negative infinity to square root of 6 over 2, and then from square root of 6 over 2 to positive infinity, you have this value here, test point, let's say 0, and then we have here, let's say 2, and we know that it is increasing or decreasing to something. Okay, so just plug in. So just recall your calculus 1. Okay, so let's forget about that and continue our topic in numerical analysis. So on open board, and g prime of x based on the graph. Okay, this one here, where are you? This one. Let's go to home. We have here increase, decreasing, that one. Okay, so we are not concerned with this point here. We are concerned with 1 to this value, and then 2 to this value to 2. Okay, so g prime of x is increasing on the interval 1 to square root of 6 over 2, and decreasing on the interval square root of 6 over 2 to 2. Okay, therefore G satisfies the condition in remark 41 with lambda is equal to, or k, okay, lambda is equal to square root of 6 over 2, square root of 6 over 2, or this is 1 point, where are you? 0.64805. 0 point 0 point not square root of 6 over 2. This would be 0 point, so that will be the x-axis, but our k here is on the lambda is on the y-axis. Our k, okay, bound for the derivative, first derivative, 0.648, okay, 648 0537 657. Okay, so that's our lambda. Okay, to answer number 2, where are you? Okay, answer number 2 of our, so our mark is, our k or our lambda is between 0 and 1. If we go to our number 2, let p sub o be equal to 1 and use corollary 42 to find n that ensures an estimate to p accurate to within 10 to the negative 4. So we will use one of these error bounds. Okay, so let's go to our open board. For number 2, we take lambda to be equal to k, which is 0.648 053 7657. Okay, in corollary 42, and use bound number 4. Use bound number 4. Okay, our bound number 4 is p minus, if you want to try it at home, you can use number 1 or number 2. It depends upon the given, is less than or equal to lambda to the n. So our lambda or k to the n is this value, 0.648 0537 657 to the n, and then max of p sub 0, which is 1. Okay, so 1 minus a, our a is 1, and b is 3 minus 1. Okay, so this is remark of corollary 42 number 4. This is a sub 0 minus, no, not a sub 0. This should be this is b minus p sub 0, and this is p sub 0 minus a. Okay, so this is equal to our max here is 2. We have 2 0.648 0537 657 to the n. Okay, and we want our bound to be, if you look at our given, accurate to within 10 to the negative 4. Okay, so we want 2 0.648 053 7657 to the power of n to be less than to 10 to the negative 4. Okay, so which implies based on our calculation before, so we can take the log both sides. Okay, take log both sides and solve for n. So what we will have here, I will not do the computation anymore, but this is very familiar to you. Okay, this is negative 4. Okay, you can use log or you can use log or ln. Okay, log natural log or common log, depends on your choice. 648 05 376 57. Okay, which is approximately 22 point no, that should be, if we go to our Firefox. Okay, negative 4 negative, where are you, negative 4 over, let's say, let's find the log first. Where are you? Log, this one, log of this number, log of this number, and then in the numerator we have log 10, log 10 close minus log log 2, log 2 close. We have 19, enter, hit enter, and 19.63. Okay, so we have 19.63, 19.63, or therefore we need 20. Therefore n is equal to 20 is the smallest number of iterations that ensures an absolute error of 10 to the negative 4. Okay, so that's the end of the solution. Okay, so that's the answer for example number 42. Okay. Okay, now we are ready to prove Theorem 38. Okay, so Theorem 38, let's go back to Theorem 38, this one here. We are going to prove Theorem 38 A and B. So let's go now to our open board, and let's this one here. So Theorem 38, Theorem, proof of Theorem 38. Okay, so first, as you have noticed, the given is our assumption is that the function g is continuous, and all the all the function values of g or g of x is also an element of the closed interval AB. So first is we have to let's consider f of x, the one that I mentioned before, to be equal to g of x minus x. And next is we are going to assume that g of a is not equal to a, okay, and g of b is not equal to b. So if in case that if they are equal, then we are done. Okay, we already have the a fixed point. Okay, otherwise the proof is over. Okay, so if g of a is equal to a or g of b is equal to b, then we are already done. So what happened if we assume that g of a is not equal to a and g of b is not equal to b? Then f of a is equal to g of a minus b, minus a, sorry, minus a. So replace this one here, the given, replace x by a. So notice also that our a and b are endpoints. Okay, they are endpoints of the interval. Okay, so notice that if g of a is not equal to a, this may happen. This implies that g of a minus a is greater than 0. Okay, it's greater than 0. You can plot the graph of the function, or it may be also that g of a minus a is less than 0, and the other one, this one here, will be greater than 0. If this is greater than 0, then this one here is less than 0. Minus b is less than 0. So either way, either of the two, this will follow. Yeah, this is greater, sorry, this is greater than 0, since g of a must be greater than a if it is not equal to a. Okay, so if you look at the graph, just like the one that I've shown you in example 42, or maybe you have more examples, either the function f of x is decreasing on the interval AB or increasing on the interval AB. Okay, so either way, if you choose g of a is minus a is less than 0, then this one is greater. If this is greater, then this one is less than 0. Okay, so similarly f of b is equal to g of b minus b. This is less than 0. Okay, and notice also that based on the assumption of theorem 38, I don't know if you recall that g of x is continuous. Okay, and the closed interval AB, and g of x is an element. All the images are element on the, also this is on the y-axis, and this is on the y-axis. Okay, am I right? Okay, for all this one here, for all x in AB. Okay, for all x on the x-axis, this one is on the x-axis, this one is on the y-axis. So since f of a and f of b are in opposite direction, okay, f of a is greater, and this is positive, and this is negative, then what can we conclude? Then by the intermediate value theorem, okay, then sorry for this one, then from the intermediate value theorem, there exists p on the open interval AB, such that f of p is equal to 0, or g of p is equal to p. Okay, so this concludes that this one by the IBT, this one here by the IBT intermediate value theorem, this will follow. Or if this is not true, then g of p is equal to p. Okay, so we proved the theorem part A. So for part B, okay, so for part B, to prove part B, suppose let's look at part B. Our part B is this one here. Okay, suppose we assume this one is inequality for all x on the closed interval AB, where your lambda is between 0 and 1. Okay, so suppose there are, we prove the uniqueness, no? So suppose there are two different fixed points, okay, fixed points P and Q. Then so P minus Q is equal to, we know that by the definition of fixed point, P is equal to G of P, and Q is equal to G of Q. Okay, and then from the definition, okay, from our definition, we know that we assume, okay, we assume that g of x is equal to, replace x by p and q by y by q. Okay, then what will happen here is that we have lambda is times the absolute value of p minus q. Okay, and we know that this is greater than p minus q, since our lambda is between 0 and 1, which is of course a contradiction. This one here is less than or equal to this one here. Absolute value of p minus q is less than absolute value of p minus q. This is a contradiction, okay, which is a contradiction. Okay, so therefore we have a, based on our theorem, the fixed point is unique. Okay, so that's the proof of theorem 38. We will go now. This is much easier to prove. We will skip that one. And for this one also, we will use this as in the Python code for the fixed point iteration, theorem 40. So as long as G is continuous on the closed interval AB, and these two are the assumptions in theorem 38, then we have this fixed point iteration. It will converge to P, and this one, the unique fixed point of G in the closed interval AB. For any starting, as long as your P sub O is an element also in the closed interval AB. So we will not prove this one. Maybe you can do it at home if you want to. This is easy. Maybe I'm going to give this one as a what do you call this one, as a problem set. Okay, and theorem 41 is also much easier to prove. As I've said before, I'm going to prove corollary 42, maybe one of these. Okay, so in the next lecture, I'm going to prove corollary 42. So let me see if I can prove one of these. Okay, so okay, this is the proof of corollary 42, number 1. Okay, so let's go now to our open board. So where's my open board? This one here. Okay, let's have this new page. Okay, sorry, this one. So this is the proof of corollary 42, number 1. Okay, so I am going to leave the rest of the parts of corollary 42 in your hands. So remember that the hypothesis of corollary 42 says that our function G satisfies the hypothesis of theorem 40. So if we go back to our theorem 40, so we have here these three assumptions. G is continuous on a continuous function on the closed interval AB, and these two also. Okay, so let's assume that our function, assume G satisfies the hypothesis of theorem 40. Okay, so note that, let's have a note somewhere here. Note that absolute value of P minus P sub n plus 1 is equal to let me put a recall here. In Theorem 40, it says that our iteration, fixed point iteration, is given by this form: P sub n is equal to G sub P sub n minus 1. That one. Okay. So, and also, since P is a fixed point, so G of P is equal to P, and P sub n minus P sub n plus 1, this one here, is G of P. Okay, this is G of P sub n. Okay, based on this one in Theorem 40. Okay, and notice that this is less than or equal to, also in Theorem 40, this is lambda 40b, lambda absolute value of P minus P sub n. Okay, let's go to our PDF, Theorem 40, this one here. Okay, so our x is P and our y is P sub n plus 1. Okay, no, our x is P and our y is P sub n. So we will use this assumption, this one here. So this is correct by Theorem 40b. Okay, and we will denote this as, let's denote this result as equation star. Okay, equation star. And that one, let's erase this. And notice that by induction, principle of mathematical induction, we can show that absolute value of P minus P sub n is less than or equal to lambda to the n times the absolute value of P minus P sub 0 for all n greater than or equal to 0. So why is this? We will use this this one here, this result. Okay, this result. Okay, let's have a bubble thought somewhere here. Bubble thought. Let's have this bubble thought. Notice that from here, equation star, we have P my absolute value of P minus P sub n plus 1 is less than or equal to lambda times the quantity, this one here. Okay, absolute value of P minus P sub n. Okay, this is from equation star. So let's try to get this one using induction. First is we have to, let's say, replace, since this is true for all n, so replace n by n minus 1. Okay, n minus 1. So what we have here is absolute value of P minus P sub n, since we replace n by n minus 1. So n minus 1 plus 1 is n. So we have here absolute value is less than or equal to lambda absolute value of p minus p sub n minus 1. Okay, again replace n by n minus 2 and replace n by n minus 3. So what we have here is p minus p sub n minus 1 less than or equal to lambda absolute value p minus p sub n minus 2. This one here absolute value p minus p sub n minus 2 is less than or equal to lambda p minus p sub n minus 3. Okay, so here replace n by n minus 1 by n minus 2 by n minus 3 up to, as you have noticed here, this will be up to replace n by 1 and then replace n by 0. So this will become absolute value of p minus p sub p sub 2 less than or equal to lambda absolute value of p minus, so p sub 1. Here we have p minus p sub 1, p minus p sub 0. Okay, so from this, notice that in here, if you start with p minus p sub n, this one here, so we will replace p minus absolute value p sub n minus 1 by this one here. Okay, so this is less than or equal to lambda times the quantity lambda p minus p sub n minus 2. Okay, so if you are going to simplify this, we have this is lambda square absolute value of p minus p sub n minus 2. Okay, and p sub n minus this one here, p sub n minus 2, p minus p sub n minus 2 we will replace by this one, and so on and so forth. Okay, this one here up to the bottom. Okay, so this is very easy to analyze. We have lambda square replaced by lambda absolute value of p minus p sub n minus 3. Okay, and this will become lambda cube absolute value of p minus p sub n minus 3. Okay, and so on and so forth, and then you will have lambda 3n times the absolute value of p minus p sub 0. Okay, so this is this one here. Okay, this one here. So this is the bubble thought. So that's how we got the formula. Here, and then let's continue up to this point. Okay, so wait just for a moment, and then so we are done with this one here. Okay, this portion. Okay, so after this, as you have noticed, we are now ready to prove corollary 42 number 1. Okay, so first we will begin with this idea. Let's have this color black. Now p minus p sub 0 is equal to p minus p sub 0 plus p sub 1 minus p sub 1. Okay, we will use the idea of triangle inequality. So by adding p sub 1 minus p sub 1, this is just 0, so this is equal to this quantity. Okay, so next we rearrange p minus p1 plus p1 minus p sub 0. Okay, p sub 0, that one. Okay, so we group and then use triangle inequality. P minus p sub 1 plus p sub 1 minus p sub 0. So from here we use triangle inequality. Okay, and then notice that this portion, the first this one here, we can use equation star. And by the way, we will denote this portion here by equation double star. Okay, equation double star. So we will use this portion, this one here, first term, we will use equation star by replacing n to be equal to 0. So when n is equal to 0, so this is p minus p sub 1, and then this will become p minus p sub 0. So this will be less than or equal to lambda times the quantity absolute value of p minus p sub 0 plus copy p sub 1 minus p sub 0. So here we use equation star. Okay, equation star. So this means this implies that if we transpose lambda, this quantity, this term, to the other side, so we will have absolute value of p minus p sub 0 minus lambda p minus p sub 0, which is less than or equal to this one, the remaining. So if we factor p minus p sub 0, p minus p sub 0, 1 minus lambda is then equal to p1 minus p sub 0. So from this, divide both sides by 1 minus lambda. So this is absolute value of p minus p sub 0 less than or equal to 1 over 1 minus lambda, p minus p sub 0. So we can remember that our lambda is between 0 and 1. Okay, so combining equation double star, and we are done. Okay, so combining this with equation double star, that one, we get, so where's our double star? This one here. Okay, so clearly p minus p sub 0, this one here, is bound by this expression 1 over 1 minus lambda. So we replace p minus this one here, p minus p sub 0, by where are you, this one here. So replace p minus p sub 0 by 1 over 1 minus lambda times p minus p sub 0. So we get absolute value of p minus p sub n less than or equal to lambda to the n times 1 over 1 minus lambda p minus p sub 0. So my right here, so we have this one. So this implies that we have lambda to the n, the right hand side is lambda to the n over 1 minus lambda times absolute value of p minus p sub 0. Okay, so this completes the proof of Theorem 42 number 1. So for the rest, I am going to leave that one to you. Okay, so that's theorem, that's corollary 42 number 1. Okay, since we are done with proof of corollary 42 number 1, and as I've said, number 2 and 3 and 4 will be for the students. Let's move now to the next part. Okay, so it says here the geometric interpretation of fixed point iteration. In figure 5, this one here, and figure 6, if we take a starting value p sub o closer to p, okay, and mark the first few fixed points iterations p sub 0, p sub 1, p sub 2, we observe that the fixed point iteration converges in the first graph, this one here, if the absolute value of the derivative is less than 1. Okay, and then if g prime, the absolute value of g prime of p is greater than 1, then it will diverge. So why is that? So notice, let's go to our open board. Where are you? This one here. Let's try another page, and let's add a document. Say, let's add a figure. Let's import something here. Let's import an image. Let's say this one, maybe this one. Okay, this one here, and make it bigger. This is figure 5. Okay, figure 5. The absolute value of the derivative is less than 1, greater than 0. If this one here is the fixed point of the function, y is called g of x, and if you start and iterate x sub 0, x sub 1, it will converge to our fixed point as long as the derivative is less than 1. But if you have greater than 1, this one here, if you have greater than 1, it will diverge, no? Example, this one here, except 0, and then it will move down again, and so on and so forth. Okay, this one here. And also for this one, the rest of the graph, there are also cases where you will encounter this kind of function g of x. Okay, so but anyway, I am going to ask you in the puzzle to create a function, or to give a function that will satisfy figure 5 or figure 6. Okay, so that's the reason why the first graph, it will converge to a fixed point, while figure number 6, the second graph, it will diverge. Okay, it depends upon the value of the what do you call this one, the derivative. Okay, so that's it for the geometric interpretation of the fixed point. And since we already done with the solution of example 42, we are now going to create a Python code for the fixed point iteration. Okay, so but anyway, you can open your Python IDLE and notice that our guess p sub o will be denoted by p0, and then computes p sub 1 is equal to, this is based on the in theorem 40, this one here. So when n is equal to 1, so we have p sub 1 is equal to g of p sub 0. So, and checks if the stopping criterion, this one, is satisfied. If it is satisfied, the code terminates with the value p sub 1. This is just the same as in the bisection, in the Newton's method or second method. Otherwise, if it will not satisfy, we will set p sub 1, p sub 1 is set to p sub 0, and the next iteration is completed. So let's go now to our Python IDLE, or Python shell, or if you have Jupyter Notebook or Spider, you can do the same, and apply this to example 43 with our previous problem in example 42, this one here. Okay, the computation by hand. So let's try to calculate, to apply the Python code for a fixed point in this in example 43. Okay, so I'm not going to solve this, but since we already discussed this in example 42. So let's go now to our what do you call this one, our Python IDLE. So I'm going to open my Python IDLE, this one here, and then I'm going to open a new file. Since I already encoded the Python code for iteration method, so I'm going to open this this one here, fixed point, this one. Okay, so this is the code for Python code for the fixed point iteration. So again, first is you have to import our package numpy as np, and then write this code here. So the same explanation as in the bisection, Newton, and second method. So this portion here is our theorem in theorem 40. Okay, p sub n is equal to g of p sub n minus 1. Again, if it will not satisfy this portion, then it will go back to the while loop until the number of iteration is achieved. Okay, if it will not achieve, then this one will print. Okay, so let's try to apply by first is to import. Let's copy this first. Let's copy this, import our numpy package first. Maybe we have a function that will need this package, and then next is we are going to encode our function lambda x is equal to in example 43, we have 2 times x squared plus 1 raised to the power of 1/3. Okay, 1/3. Okay, so that's our function. Let's recall this one here. Okay, this one, 2x squared plus 1, and then our p sub 0 is equal to 1. Our tolerance is 10 to the negative 4 and n is equal to 30. So let's go now to this one here. Sorry. This, okay, so this one, what happened? Where are you? This one, and hit enter. Okay, and then where is this one here? Okay, then copy this first. This one. Okay, sorry, we have to run this first. Okay, and then copy. Okay, and then enter, and then copy, enter, and then copy this one. Okay, and then we have p sub 0 is equal to 1, and our tolerance is 1 times 10 to the negative 4, and our n is 30. Enter. So our fixed point is 2.2. This one here, 2.20547. Okay, this one here. So let's copy this first. Copy that one, and then the iteration is 19, but based on our calculation, we have, oh, not this one, in our open board. Let's go to our open board and go to, I think, this one here. Okay, this one. For our open board, we compute our n to be 20, which is closer to, of course, closer to our calculation. In the Python, we compute n is equal to 19. Okay, so we are close. So let's go now to our Firefox browser, and let's go to our Dismos graphing calculator, and then let's plot our function 2x squared plus 1 raised to the power of 1/3. Okay, that one, and then our y is equal to x is that one, And then notice that our answer is 2.2 something. And clearly in the graph, if we want to zoom in, zoom out something, it's clearly the fixed point is this one. Okay, and our function is let's go to our PDF. Based on our calculation, where are you? This one here. This one. G of x, our function is, our f of x is x minus g of x. Okay, so x minus, if we copy this one here, so we enter, clearly the root of our f of x, no, not that one, this is not one, our f of x is x squared, sorry, let's go to f1, where are you? Our f of x is, where are you? This one, x cubed minus 2x squared minus 1. Okay, x squared minus 2x cubed, x, not x squared, x cubed minus 2x squared, 2x squared minus 1. Okay, so enter. So notice that our root, our fixed point problem can be converted to root finding. Okay, just like what I have discussed in the, you can convert the fixed point problem to what do you call this one, to root finding problem. Okay, so that's the graph of the function, and maybe you are tempted to do the other way around, like isolating 2x squared and computing for x. Okay, you can do that also, but be sure that the interval 1 3 will satisfy. Okay, so that's it for example 43, am I right? Example 43, this one. Okay, so the next is the exact value of the fixed point equivalently the root of x cubed, this one is this, as I discussed, and the error is if you let's say, let's go to our f4 and then try to get the difference, this one here, copy, minus where are you? Minus, skip this one here. So what would be the error? What would be the error? This one. So the error is small enough, as you can see in the calculation. Okay, so that's it for let me see, we have, this is correct. Okay, that one is correct. Okay, this is the error, this portion here. Let's go back to F1 and then notice also that this message here, the exact error p sub n minus p is guaranteed to be less than, as I've shown you, after the 23rd iterations from, not 23rd, but this is how many iterations, okay, from corollary 42. This is not 20, but this is 20, sorry, but this is 20. But as we observe in this example, this could happen before 20 iterations. So I'm going to replace this, or anyway, replace it in your notebook. This is 20 iterations based on our calculations in corollary 42 number 4. Okay, and number 2, as a word of caution, the stopping criterion used in the code is based on this one, not this one. So the iteration number that makes these quantities less than a tolerance epsilon will not be the same in general. Notice in corollary 42 there are 4, as you can see here, there are 4 bounds. We use this one here. Okay, so maybe if you use this number 1, number 2, number 3, it will be different. Okay, so be careful in what they call this one, be careful in stating your conclusion. Okay, theorem 44, this is the last. Assume p is a solution of g of x is equal to x, meaning to say that this is a p is the fixed point, and suppose that g of x is continuously differentiable in some open interval about p with this inequality, then the fixed point iteration converges to p provided p sub o is chosen sufficiently close to p. Moreover, the convergence is linear if this one is true. Okay, so you can find a proof in the internet, or maybe I'm going to give this one as a problem set. Okay, so that's it for this topic. Maybe if you cannot discuss further because of time constraints, can visit my my YouTube page, YouTube what do you call this one, YouTube to watch more videos. Maybe I will upload more videos in chapter 3, chapter 4, and chapter 5. So I hope that you will try to learn more in the next succeeding time. Okay, thank you so much for listening. I'm going to give a problem set later.